Multiplicity and special roots. Now, those are the same thing. Like these special roots are described using multiplicity. So start with that word multiplicity. What's in that word multiplicity? Multiple. When you have multiple things, what's usually happening? Well, you multiply. So that's one thing. So multiplying. Where do we multiply in our equations? Like, for instance, this asks us to write in a certain form. What form is that? So what's multiplying there? The parentheses, the factors, right? They're multiplying by each other. And I also heard the word multiple, right? What does it mean when there are multiple things? More than one, right? So a multiplicity, remember, it's always important to like drill into these words, because then when we see it, we don't have to be like, wait, what does that mean again? You just understand the pieces, right? There's going to be multiple things happening, right? It's a multiple of something. And then also there's going to be multiplying, right? So there's things that are multiplying and maybe multiple times, right? So that's all there in the word. And that results in special types of roots or special situations, right? And just like knowing our degree, knowing our reflection, knowing all those things helps us graph something, helps us understand something. Knowing a multiplicity can help us. It'll just add more information to what we've been doing, right? So that's what we're going to do today. So for your warm-up, you were given two cubic functions, right? Meaning degree 3, right? And you were asked to figure out the roots and write them in factored form as much as you could, right? So if you're looking at these and you're trying to find the roots, we'll just zero in on this one, right? Well, how do I find roots by looking at a graph? Looking for x-intercepts, right? If they're there, right? Remember, we're going to get to a point where not every root is an x-intercept, just like with parabolas, right? Where there was imaginary roots, right? But we're not quite there yet. But for now, sure, x-intercepts. So if I'm looking at this graph, right, what x-intercepts do I see? I got -2, and what else? 1. So if I'm talking about my roots, I got -2 and +1. Okay. Now, this asks us to write in factored form, right? So if I'm writing in factored form, well, I got to think about my degree, right? Now, let me back up. A lot of times, we've been writing in factored form for weeks, right? A lot of times, to get our factored form, we factor, right? We use grouping, or we use quadratic form, or we use GCF, we use magic X. We get it into factors. That's factored form. But we also very early on talked about doing it from a graph. When you see your roots, right? And you can just say, well, those are my factors. And you can write them as factors, right? Now, I want to think about my degree to think about how many factors I would have, right? If I have a cubic function, how many factors should I expect? 3. And factors are usually written as those, what? Like a root is just -2, but a factor would be x and then a number, right? So how many should we have for a cubic function? 3. And they're parentheses. And remember, factors are things that multiply by each other. So that's why it's called factored form. I have a factor times a factor times a factor. Now, usually we just take our roots and we change them to factors and we put them in, right? So let's do that. We have, my first root was -2. So what's the factor that goes with that? X plus 2. And then I have 1. What's the factor that goes with that? X minus 1. What's the problem here? I'm missing a root, right? I only have 2 roots. I'm supposed to have 3 factors. So we got a special situation. This is one of those special situations, right? So let's take a look and see if we can try to just figure this out. Maybe we'll remember some things that were briefly touched upon, but we didn't totally drill into them yet, right? What do we notice about -2 and 1 on the graph in terms of what's similar and what's different in those situations? What's happening at -2 if you're just thinking of like the path of the function. Yeah, go ahead.
-2 crosses.
Yep. Just crosses right through the x-axis, right? And then at 1, or it's not 1, yeah, 1. I don't know why I'm second guessing myself. At 1, what happens? Yeah.
It bounces.
Yeah, it's almost as if you're looking at it as a travel bounces right off, right? So there's two different things that are happening. Which one of those feels like a special situation? Like a situation that doesn't always happen?
The bounce.
The bounce, right? The 1, right? So that is an indicator we have a special root. When we have a non-normal behavior, it's not just crossing, it's bouncing, or we'll talk about another thing that can happen, right? So that would be our special root. Does anybody remember what happens at that point? What do we, or have a guess? Yeah, what do you think?
It might be. Wait, there's a second x.
So it might be a double root, right? Now, why? Let's think about why that might happen. Now, let's talk about the graph of like y equals x minus 4 squared, and let's think all the way back to parent functions, right? And with our parent functions, we were like, all right, we're not worried about roots yet. We don't even use that word yet. We're just like, okay, I know what the parent function does, and I know what the transformations that happen are when there's things on the inside, when there's things on the outside. This was a while ago, though, right? The parent function of y equals x squared would just be right here, right? And then minus 4 on the inside tells me what?
Minus 4.
What does a minus 4 on the inside tell me to move the parent function?
4 to the right.
4 to the right. So I would go to 4, and then I would have this situation, right? Okay, well, now that we know what roots are, now that we know what the different situations are, what are the roots of that function? The root, if I made y 0, would just be 4 twice, right? And what happens at that point? It's a parabola that does what at 4?
Intercept.
It's got to intercept, but does it cross?
No.
No, it bounces, right? So we've seen this before, right? We've seen this bouncing before, okay? We just thought of it as moving around. Now we understand it as roots, right? So, yes, indeed, there is a second root at x minus 1, and that makes this a double root. And we're going to define what happens at double roots, but let's notice it first, right? We got this bouncing situation, okay? Now, that makes -2 a single root, right? And that matters too, because at a single root, we should expect the same behavior all the time. What behavior did we say happens at a single root? What does our normal root do? It just crosses, right? And at double, turns out, looks like we bounce, okay? Now, here's a little bit of a check that we can do to make sure that we're not just guessing and figuring this thing out. What if I told you, okay, what if I didn't tell you this? When I tell you what the other root was, and I told you, and you knew from your experience, you know you got at least x plus 2 and x minus 1 there, but this part was still a question mark. How could you start to factor to find that other root? Find that other factor. So for instance, pick one. Which one of these do you want to pick, x plus 2 or x minus 1? What's that? Plus 2. Okay, so we can make the statement, we know at the very least x plus 2 is a factor of that. And I asked you the question, what are the other factors? Because if we find them, we could prove that x plus 1 is our missing factor, right? We actually already know one, but we're just going to start with one piece, see if we can build to other pieces. How could I start to factoring knowing one factor? Without a trick, without any like magic X or anything like that. Remember on your graphic organizer, I put it on the bottom. I said, When in doubt, you could always factor using a graph. Well, we tried that. We didn't have enough information. Or what? When we're factoring, what are we doing? We're saying, like if I'm factoring 6, I keep bringing up this example because it's a simple example, right? Factoring 6. Well, let's say you forgot the factors of 6, but you knew 2 was 1. How could you find the other one? Divide 6 by 2. So now I'm telling you, you know x plus 2 is a factor. You want to find the other one. You should divide f of x by x plus 2. So we're going to divide f of x by x plus 2 and see what we get. And this is an important skill that we need to start building, right? Because we're going to actually tomorrow and going forward have these unfactorable, in other ways, things that we can only do through this division. And when we divide, we use what? What's our method for dividing big polynomials? Synthetic division. So let's see what happens when we do this, because we should be able to come up with these other factors. All right? So if I got x plus 2 is my factor, my root that I'm testing is negative 2. And on the inside, I'd have 1, 0, very good, negative 3, and 2. And guess what? I know for a fact it's a factor, so I can already expect what? Right here, a 0 remainder. Very good. All right, so let's see what happens. We'll knock out our synthetic division, bring down the 1. I get negative 2, 4, 1, negative 2, and there's that 0. So we got it correct. Okay, now what did we just figure out? Remember, we're trying to get factored form here. What did we divide by? What was the factor we divided by? X plus 2. And what do we know is our other, what's the remaining piece of this now that we've divided? Well, the remainder was 0, telling us that we have another factor of, like if you divide 6 by 2, you get 3. We divided ours by x plus 2, we got x squared minus 2x plus 1. Okay? Now, what do I want to do? I want to continue to factor. So how do I factor this? Very good. I would magic x. I got 1 on the top, minus 2 on the bottom. What's the only way for that to happen? Minus 1, right? Okay, so now this becomes f of x equals x plus 2, x minus 1, x minus 1. There it is. There's that double root. So we can prove this to ourselves, or if we forget it, we could find it using synthetic division. And we would simplify this. We'd say f of x equals x plus 2, and then x minus 1 squared. Okay? So we now have discovered that indeed there is a double root at 1, right? We saw what happens on the graph. We proved it to ourselves with synthetic division, right? Got a little practice in factoring using synthetic division along the way. That can hurt. Okay? All right, let's look at the other one. Here, well, I got an even more complicated situation. What are the roots that I see? Just 2, right? Positive 2, right? And I'm still supposed to get to this cubic function of f of x equals x minus 2, and then 2 other roots, right? What do we think might be happening here?
I mean, I think it might be a triple.
Yeah, that's a good prediction, right? Because we're talking about multiple roots, and clearly there's something going on here, and we got one of our roots, so x minus 2 and x minus 2. Okay, how could I test to see if that actually turns out to be true?
Go back to the equation and figure it out.
I'm giving you the full equation. You know one root for sure. What could you do to make sure that these are the other 2 roots? Divide, synthetic division. Okay? So take a moment now, try that. Try to use synthetic division to prove that the other 2 roots must be this and this, right? This is what we know for sure. And that must be the result if we divide.
We don't switch this sign yet.
You definitely switch the sign because that's a factor. So you'd put 2 on the outside of your synthetic division. Oh, so you mean from the root? No. Yeah, keep the sign.
Isn't it the same thing?
What do you mean?
Like x minus 2 and x minus 2 and then x minus 2.
Well, when you divide by this, you should get a trinomial. Then you need to factor using magic x. Okay, give it a shot, and then we'll go over it. All right, is anybody still working? Okay, so again, we knew for sure we had one root, right? So we used synthetic division to continue factoring just to see if we could find the other roots, even though we had a guess that there were probably 2 more x minus 2s. We divided. We got this as our result, so we know that the function is this times this. Then we were able to use magic x to continue to factor this, right? And that gave us minus 2 and minus 2, which is x minus 2, x minus 2, x minus 2, or x minus 2 to the third, right? Proving that indeed 2 is a triple root, right? So this is 2, turns out is a triple root. Okay, and now we want to look at the graph and see what do we notice is happening at 2. It's not just crossing, right, like a single root. What else is happening there? Yeah, there's a change, right? It's like going up, up, up with curve down, and then it starts to go up, 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 curved up, right? So it's still going up. Doesn't change from down to up like happened at our bounce. But there's a change in what's called concavity, which is the shape of the curve. Is the curve facing up or down, right? And that will happen when you have a triple root, okay? So this is the noticing. Now we're going to define it, okay? So let's go down to the bottom and define it. And then we'll use it to help us graph a couple functions, and then that'll be it for the day, okay? So multiplicity. Let's define multiplicity and then talk about our 3 scenarios that we're going to have here. So first of all, multiplicity is a couple things, right? First of all, multiplicity is the number of times a root or factor exists, right? It's the number of times you're multiplying a factor or the number of times your root exists, right? It's also the number of the exponent attached to a factor. And there's more than just 3 multiplicities. We're only talking about 3 in this class, right? We're going to get to 3, okay? Now, the first one we know very well already. We just maybe never thought of it this way, okay? Our first one is single roots or factors. And this would be what we would call a multiplicity of 1. And we're going to look at an example that we're kind of just going to keep changing as we go. This would be a multiplicity of 1, and our example will be y equals x minus 2 to the 1. So there's a factor. It shows up once. It's to the 1. Now, do we usually write to the 1? No. I would just write x minus 2. And in fact, I probably wouldn't even have parentheses. I would just have y equals x minus 2, which is what type of function? Y equals x minus 2. Just no squared, no cubed. It's line, right? And it would look like this, right? Okay? Now, this is an example of a single root, right? We just have the one root at 2. And this behaves at the x-axis the same way every time you have that one root, that one singular multiplicity, okay? And we talked about it already. This just crosses the x-axis, and there is no change in direction or concavity. Right? Anytime you get a single root, that'll happen, right? It's not always going to be a line. Sometimes it's just like in our first example. In the first example, there was x plus 2. It was by itself, so we just crossed. Okay? Okay, so that's our first one. Our next one would be a double root, right? So double roots or factors have a multiplicity of 2, right? And we're going to extend our example. So instead of x minus 2 to the 1, we'll say x minus 2, well, y equals x minus 2 to the 2. So we know there'll be a double root at 2. And x minus 2 to the 2, what kind of graph will that be? Something squared. What does a squared graph look like? It's a parabola, right? And we talked about this example kind of a little bit already, right? It'll bounce, right? And that happens in the middle of a function too, right? Just like in our example in warm-up number 1, right? So every time we get that double root, we say there's no cross, and I like to say it bounces off the x-axis, and it changes direction. Okay? So it comes down, bounces off, changes direction, because we got a double root. Okay? Which brings us to our last version that we're going to see in this class, which would be a triple root or factor. And we say that this has a multiplicity of 3. And we're just going to extend our example again. Y equals x minus 2 to the third. So now I have that same root at 2, but what type of function is to the third? Cubic, right? And a cubic function that is just moved to the right 2 would come up and then go through 2 and change its concavity, right? So we'll define that word concavity before we go, but let's first talk about these triple roots. They always cross the x-axis, and they change their concavity. All right, so let's talk about the word concavity. Do that over on the side here. Concavity. So you can either be concave up, meaning like you could hold water. If you're concave up, the curve is facing up. Or concave down, and like the water would fall out, right? Oops. Right? It wouldn't hold anything. That's concave down, right? So if I'm looking at this, well, it's really curve down or curve up. It's this thing starts out concave down, like curve down, and then this part concave up, right? You could see how, well, if this went all the way like this, it would hold water, right? It's like, is the curve facing in a position where you're cupping your hand up or you're cupping your hand down, okay? That's what you want to think. That change in concavity will happen every time you have a triple root, right? It'll cross, but that concavity change will happen. Okay? So that's what we need to be prepared to do on a graph. Okay. So let's look at some examples. Now we're going to do what we've been doing, but we're just going to add these pieces to help with our graph. Okay? So let's take a look. All right, so here it says find the roots and sketch a graph, right? Well, finding the roots we know how to do already, right? We set equal to 0, and then I start to work on factoring, trying to find my pieces, right? Here I see a GCF, so I'm going to pull out x squared, and then I have x squared minus 5x minus 14. Now that part I can magic x, and I'm going to go a little quickly through this since this is not the new part to make sure I have time. Now, minus 14 minus 5, that gives me negative 2 and 7, right? Oh, sorry. Positive 2 and negative 7. Okay, so I throw those in. 0 equals x squared, x plus 2, x minus 7. Now I'm at the zero product property part, so I pull it apart. X squared equals 0. X plus 2 equals 0. X minus 7 equals 0. I'm looking for my roots, right? So I solve each of these. I find out x equals 7. X equals negative 2. And then for this one, think about what you would do. You would square root both. You would get x equals plus or minus 0, which isn't really important in that plus 0 and minus 0 are the same thing, but what does it tell you? There's 2 roots there, right? It's a double root, right? Because it was x squared that got us that. That's 2. There's 2 roots there, right? So this is a double root. This is a single. And this is a single. All right? Now, before we graph this, there's a couple things we want to think about. First of all, if I have a positive x to the 4th graph, what's that going to look like in terms of its end behavior? Top, squiggly, back to the top, right? So we like to sketch first so we know that our final product will look like that, right? Question?
But didn't you say last time it's just x squared, you just put it equal to 0 and that's it? And you didn't tell us like what?
Well, yeah, we're adding the piece here now. Yeah. So we didn't have that information yet. So, okay, another thing that I think is helpful for students is if you make a roots multiplicity table. So I'm going to go roots multiplicity. Right? And I'm going to list my roots. I have negative 2, 0, and 7. And then I say, okay, negative 2, that's a single, so that'll cross. 0 is a double, so it'll bounce. 7 is a single, so it'll cross. Then I add those roots to my graph. I got one at negative 2. I got one at 0. And I got one at 7. And when we're sketching, we're just estimating, right? Now, the other thing you want to keep in mind is your y-intercept. But here, our y-intercept is 0 because we don't have a c, right? So that doesn't, it'll come up more in the next problem. All right, now we got to take our graph on a journey. And that's why the sketch really helps, right? Because I know from my little sketch on the bottom where I'm going to start. Where are we going to start? Where does this x to the 4th always start? If it's positive.
It goes up.
Well, it starts at the top, right? So I'm taking this journey from the top, right? Okay, then I need to go to my first root. What happens at negative 2?
It bounces.
No, at negative 2, I made my chart. It says it just crosses. So I'm going to cross through negative 2. All right, now I think about what happens at my next root. It must bounce. Since we're on the bottom side, it's going to bounce and come back down, right? So I'm going to go boom. And then what happens at 7?
It's a single one, so it crosses.
It crosses, and that's good because we were trying to get back up. And I have my graph even more accurate than I have in the past. Now, you might be wondering, how do I figure out what goes on in here? Well, if you want to add points, what could you do? If I want to know what happens at 4, I could use synthetic division, look for my remainder, and find the y value. You could find these points along the way. I won't expect that yet, but if you want, you can continue to add points, right? Okay, so this is your method. You got to use your factoring and solving methods, and then at the end, you got to be like, oh, I got a double, I got a triple. Make a little chart for yourself if that helps, so you know what happens at each. You need to have an idea of what the shape's going to look like, and then take it on its journey, just looking for everything along the way. Okay? So, you have 2 more problems to do. So, I want you to work on them now. Ask questions if you need to. I will put up the results to them. We only have about 5 minutes, so I'll put up the results to them on OneNote if you want to see how you do. Probably able to check in with them a little bit at the end. And then one thing I want to note before you go, that the other piece that is really important is this last number here. What is that?
That is your y.
That's your y-intercept. That's another point you should be able to get through. Right? So add that when you add your roots. And you should, if you do the journey correctly, you should be able to get through that point pretty easily. Okay? All right. I'm going to hand out your homework while you work and ask questions. Okay?